This diagram shows an air-cooled chiller supplying chilled water to the air handling unit. Supply air is delivered to two thermal zones. The zone on the left with more people having higher cooling loads, the other having lower cooling loads. The zones are regulated by a variable air volume (VEV) system that controls the amount of conditioned air delivered to the zones. By opening or closing the damper in the VEV box, the volume of the supply air at a constant temperature, typically 55 degree F, is regulated according to the zonal thermal load. The thermostat in each zone sends signals to the VEV box to open or close the damper based upon the needs of the zone. In this case, the VEV box on the left zone opens more to introduce more cool air, whereas the VEV box on the right opens less to emit less cool air. Stale air from the space is returned to the air handling unit by ductwork. A portion of the return air is released to the outside as exhaust, and fresh air is emitted from outside into the air handling unit to maintain air quality in the building. The supply air can also be heated in the air handling unit by the hot water coil that connects to a boiler, which is not shown in this diagram. To maintain air quality, a minimum amount of fresh air needs to be delivered to each zone in any case, under certain ambient and occupancy conditions, such as when internal gain becomes very low in a north-facing room without solar gain. Even when the damper is close to its lowest level, only enough for fresh air, the room temperature still falls below the set point. In this case, occupants will feel cold. This creates a need to reheat the air to a warmer temperature to ensure comfort. Reheat can be achieved by perimeter heating, such as fin tubes or radiant panels, or by providing reheat inside the VV box. The source of reheat in VV box can be an electric heating element or a hot water heating element, such as in this diagram. The thermostat and the controller will turn on the reheat element only when the zone is under the above-mentioned condition. The reheat component in VV enhances thermal comfort, as it is only used when and where it's needed. The energy penalty for reheat is considered as reasonable. However, it certainly increases installation and operation costs compared to VEV without reheat. In general, VEV is highly flexible in controlling many zones in large buildings. It can achieve some of the highest levels of energy efficiency in the market because it primarily relies on changing air volume to respond to zonal loads rather than on changing air temperature. Now let's look at some scenarios of implementing the VEV system in a 3-story commercial building. This is a scenario with the central air handling unit on the roof served by a water-cooled chiller. The cooling tower cools the condenser in the chiller. The chiller provides chill water to the air handling unit. A boiler in the basement provides hot water to the air handling unit for heating. Supply air is delivered to the spaces below by vertical ducts and horizontal ducts. Each thermal zone is regulated by a VV box controlled by the thermostat in each zone. In this example, there is no reheat element in the VV box. Stale air is returned to the air handling unit by ceiling plenum and vertical return ducts. Both vertical supply and return ducts are in the shaft that goes through the top 2 floors. To maintain the air quality in the building, a portion of the return air is released to outside as exhaust, and fresh air is emitted from outside to combine with the rest of the return air to be reconditioned and delivered to the space. Since all major equipment, the air handling unit, the water-cooled chiller, and the cooling tower are all located on the roof, this design can free up the valuable indoor spaces. The cooling tower and the air handling unit also have a good access to outside air. In this example, the air handling unit is located in a mechanical room in the basement. An areaway is provided so that the air handling unit can have access to fresh air. The water-cooled chiller and boiler are also located in the mechanical room in the basement, providing chilled water and hot water respectively to the air handling unit. A cooling tower is located outside of the building, on the roof in this case, to cool the water in the condenser water loop. Room temperature is regulated by variable air volume, as in the last example. This design greatly frees up the roof for roof patios, green roofs, etc. The central air handling unit can also be located on a floor above grade, in which case it is desirable to place the unit in a mechanical room adjacent to an exterior wall. Louver areas should be provided on the exterior wall for fresh air intake and exhaust. In this example, the air handling unit is located on the first floor. The water-cooled chiller and the boiler are also located in the same mechanical room, providing chilled water and hot water to the air handling unit. A cooling tower is located outside of the building, on the roof in this case, to cool the water in the condenser water loop. This design provides easy access to the equipment from the ground level for repair and replacement. Noise reduction strategies should be in place to isolate the noise generated by the air handling unit and the chiller from the rest of the floor. In this scenario, an air handling unit is installed on each floor to service the space on that floor only. Vertical air supply and return ducts are eliminated in this scheme. Instead, energy is distributed vertically across the floors by insulated chilled water and hot water piping. This can lead to significant energy savings because water is more efficient than air to distribute energy. It is desirable to place the air handling unit on each floor in a mechanical room adjacent to an exterior wall, so that louvers can be installed for fresh air intake and exhaust. The water-cooled chiller and cooling tower are both located on the roof in this example. Energy efficiency can be greatly enhanced by the elimination of vertical ducts, shortened duct runs, and reduced fan power in the scheme. However, the air handling unit on each floor takes up assignable spaces. Noise reduction strategies should also be in place to isolate the noise generated by the air handling units and the chiller from the rest of the floor. This example features a VEV system in an underfloor air delivery system. The central air handling unit is located on the roof, supplying air through vertical ducts to a horizontal manifold at each floor, where feeder ducts connected to the manifold send supply air to pressurize the underfloor plenum at each level. VEV floor boxes regulate the air volume and deliver air upward into the space. Air is returned through the seating plenum and the return manifold back to the air handling unit. The underfloor air distribution system can also be coupled with a scheme in which one local air handling unit is provided at each floor to reduce duct run and fan power. As discussed previously, direct expansion is a system where supply air passes directly through the evaporator in the refrigerant cycle without involving any chilled water. A DX unit is typically less efficient than a chilled water system and involves more maintenance. They are usually used for smaller buildings. To serve a larger building, multiple DX units are needed to provide heating, cooling, and ventilation to different areas of the building. In this example, the DX units are located on the roof, each serving a portion of the building, by separate sets of ductworks. In this design, DX Unit 1 serves the basement. Unit 2 serves this portion of the building facing a solar orientation, and Unit 3 serves this portion of the building facing another direction. A dual duct system has both warm air and cold air from the central air handling unit. The two air streams are separately ducted to a mixing chamber with dampers controlled by the thermostat at each zone. Both warm air and cold air are modulated and delivered to a zone with variable air volume and variable temperature. For example, a large amount of cold air and a small amount of warm air are mixed into an airstream at 60 degrees F and delivered to the zone on the left with higher cooling loads. A smaller amount of cold air and a larger amount of warm air are mixed into an airstream at 70 degrees F and delivered to the zone on the right with lower cooling loads. Thermostat controls the dampers in the mixing chamber to regulate the amounts of cold and warm air being mixed. Return air is handled through a single duct system or through sealing plenum, such as in this example. This diagram shows an example of a dual duct system in a multi-story building. The water-cooled chiller, cooling tower, and air handling unit are all located on the roof in this case. The boiler and chiller supply hot and chilled water to the air handling unit to generate hot and cold air simultaneously. The two air streams are distributed in two parallel ducts, from which a mixing box controlled by the thermostat of each thermal zone draws both types of air and mixes them according to the thermal load required in the space. Stale air is returned through sealing plenums and vertical ducts back to the air handling unit. The advantages of dual duct systems include good temperature and humidity control and excellent indoor air quality. With two banks of warm and cold air available simultaneously, it can accommodate a wide variety of zone loads. The disadvantages include high installation costs, space needs for ducts and mixing boxes, and high energy consumptions. Dual duct systems have become uncommon due to its poor energy performance, except in hospitals where high levels of thermal comfort and air quality are desired. A constant air volume system provides a constant volume of air to all zones. A reheat element is added in the ductwork for further temperature control at each individual zone. This allows for some spaces to have different supply air temperatures than others. In this example, a fixed amount of conditioned air at 55 degrees F is delivered to both spaces. The reheat coil in the left zone operates in lower capacity and thus provides cooler supply air than the other zone because the left zone has a higher cooling load. Regardless of the zonal thermal load, the volume of the air delivered to any zone is at a constant rate. Constant air volume systems are relatively simple and therefore have a lower initial cost. They are well suited for applications where the thermal load is constant for large periods of time, such as warehouses, where the number of occupants and thermal requirements show almost no variation. When a constant air volume system is used in a large building with varying thermal loads, reheat is needed and is constantly in use to regulate the building climate. This results in poor energy performance because the building is constantly in cooling and heating simultaneously. In a CAV system, the airflow volume is fixed. When the full design airflow is not required, it is impossible to reduce it. This feature makes the system less energy efficient as well.